Well, folks, it's time to kick it old school. So you can feel cool.
Hey guys, this is Andrew with HKN, and today I'm going to be doing a problem that's kind of a mix from Circuits 1 and from Signals and Systems. You'll be able to find this in either class. So what we're going to do is we're going to take an input signal to the circuit U of t, and what we're going to be looking for is we're going to be looking for the output voltage here, Y of t. And we're going to do that by relating these two using a transfer function. And a transfer function basically is the output divided by the input, but not in the time domain, in actually the Laplace domain. So we're going to have to be taking some Laplace transforms and stuff like that. And it's fairly easy to go directly from the circuit using some of our knowledge of circuit analysis to the transfer function. So we're going to do that today. So the first thing I want to talk about is down here is we have our voltage and current relationships for inductors, capacitors, and resistors there. But if we're going to do this, it would be nice if we could treat all these things as resistors, because doing Kirchhoff's voltage law and Kirchhoff's current law using just resistors is fairly easy. And if we can do that, it would be great. So what we're going to do is we're going to take a Laplace transform of all of these and see what we end up getting to see if we can treat everything as just a scalar. Because what Laplace transforms tend to do is they tend to take derivatives and integrals in these complex calculus topics and take them to algebra. So that would help us a lot. So the basic fact we're going to use is that the Laplace transform of the derivative of a function is just s times that original function in the Laplace domain, assuming that the initial condition is 0, which we will assume for this problem. If not, you have an extra term. So if f of 0 is not 0, we need to subtract off that initial condition. But like I said, assuming this problem, we're going to assume that we have an initial condition of 0. So this is the one we're going to be working with. So if we look at this one here, what we find is that we have Ls of IL of s is equal to VL of s. And so this looks like a good current voltage relationship, because once we have the current, all we have to do is multiply by this term out here, Ls, and we get the voltage. So what we call this thing here is we call this the impedance of an inductor. If we do the same thing, carrying on down here, we get that we have CS VC of s is equal to IC of s. And so this is not in the same form you see here. What you see is that we have the voltage on one side over here, and the current is being multiplied. But here we have the voltage multiplied. So what we want to do is we want to divide that over so that we have everything in the same form, just relating current to voltage by a multiplication. So we do 1 over CS here, and we call that our impedance for a capacitor, ZC. Now we're going to do it for the resistor, and actually this one's fairly easy. So we know that we have VR of s is going to equal to constants under a Laplace transform, just become constants. So we have R times IR of s. So the impedance of a resistor is actually just its resistance. So most of the time we don't call it the impedance of a resistor, we don't call it ZR. We'll generally just call it the resistance, because it doesn't change in either domain. So now that we have these things, we can treat these resistors and capacitors and inductors, these complex time derivative varying things, as just kind of resistors. And so we're just going to box them all in, because we can treat them all as the same element. We just have to make sure that we use the correct impedances for each thing. So now what we're going to do is we're going to do Kirchhoff's voltage and Kirchhoff's current law at a bunch of different nodes and a bunch of different loops so that we can relate Y to U. So let's make sure that we can do that. So the first thing we're going to do is we're going to realize that we have two essential nodes here. We have V, we'll call this VA, and we'll call this VB. And the first thing we're going to realize is that the voltage at B, VB, is equal to our output voltage Y. So if you see the voltage across these two, assuming that this is going to be ground, I should always tell you that when we're doing nodal analysis, I define ground to be the bottom. If this is ground, then the node voltage VB is the exact same as our output voltage Y. So what we're going to do is we're going to apply our nodal analysis techniques here, and we're going to assume that all the current enters the node, and if it doesn't enter the node, then it's negative. So let's do our nodal analysis methods using, instead of the derivatives and stuff like that, we're going to plug in our impedance values for this so that we can get a transfer function quickly. So I guess one other thing to note is that the node voltage here is just U of S. So let's do the node voltage for node VA. So for node VA, we have our input, U of S, and we're going to subtract off VA, and we're going to divide by 1 ohm, and that is for this current here. Where it's coming from, subtract where it's going to, and divide by the impedance. Then we have down here to up here, and we are going to divide by the total impedance on that branch. So we have 0 minus VA divided by 1 plus 1 over 2s. Now we have the last one here, which is this current. So we're going from VB to VA, and we're going through this inductor. So we have to do plus VB minus VA, and we're going to divide by LS, which is just 1s, so we're just dividing by s. And these should all sum to 0. So now what we're going to do is we're going to put this in what we call standard form, which is just one term times VA plus another term times VB equals everything else. So what we have here is we have just one VA, and then we have a 1 over S VA, so our negative, and then we have these guys here. So what we'll do is, specifically for this one, we'll multiply top and bottom by 2s. That'll probably make our life easier, and then we'll simplify. So I'm going to do that all in one step. You can work out the math for yourself. So we have a minus VA, and then we have a minus 2s divided by 2s plus 1 VA, and then we have a plus 1 over s, minus a 1 over s VA. And then our VB terms here are just plus 1 over s VB. And that's all going to still equal to minus U of S. Sorry for the different ways of writing my U. These are the same thing. And then we're going to combine here. So we have a minus 1. We have minus 1 minus 1 over s, and then we have minus 2s over 2s plus 1, all times VA plus 1 over s VB is equal to negative u of s. And so I don't like this equaling negative u of s just because it seems weird. So we're going to flip the signs of everything just for a sanity check. Plus, plus, plus. OK. So now this is very hard to work with. This is a bunch of different terms added together. So what we're going to do is we're going to make this one giant fraction. And then we'll be done with this node voltage. So the way that we do that is we're just going to multiply everything by the common denominator, which is 2s squared plus s. And then we'll cancel as needed. So we get 2s squared plus s for this 1. And this is all going to be divided by 2s squared plus s. We then add a 2s plus 1. And finally, we add another 2s squared. And so if we combine terms here, two of the 2s squareds here can combine to a single 4s squared. So that's convenient. So end up with 4s squared. And then we have an s and a 2s in the middle here. So this is going to combine to 3s plus 1. And I guess we can leave the bottom here factored as 2s plus 1. 2s plus 1 times s. Sometimes that's easier to see. And it's all times VA minus 1 over s VB. And this is all going to equal to u of s. So what you can notice here is if we sub in y here, we should be able to write u and y, but we have this extra term VA here. So if we have two unknowns, what we need is we need another equation. And the way that we're going to get that other equation is by doing node voltage at node B. So we're going to make sure we remember this equation. I'm going to write it down up top here. So we have 4s squared plus 3s plus 1, all divided by 2s plus 1 times s VA minus 1 over s VB is equal to u of s. So we're going to remember that one, and then we're going to clear up some space, and we're going to do node B. So clearing up some space very quickly. And this is very useful, again, so if you watched our videos on creating state spaces and stuff like that for these circuits, it lets you relate any input to this circuit, assuming 0 initial conditions. It allows you to relate any input to any output, assuming that it's a stable input, which means that you're not just ramping it up to infinity, which in reality will not happen. So now we're going to look at node VB here. So looking at node VB, we're going to do nodal analysis again. So we have VA minus VB over LS. So we have VA minus VB all divided by S. So then we have this current here, which is 0 minus VB over 2. We get minus VB all over 2. I'm leaving off units here because the units end up being some weird combination of radians per second and ohms, and it just confuses things, so we're going to get the units right at the end. But what's nice about a transfer function, because it's a voltage divided by a voltage, it's actually unitless. So assuming we did everything right, we shouldn't have to worry about units at all here. And so finally, we have this current, which goes from down here, the other edge of the two components, which is 0, to VB. And we then have to sum these together. So we're going to get a minus VB divided by, so we have 2s, and then we have plus 1 over s. And this should all equal to 0. All right. So now we're going to do the same thing that we did for up there. We're going to write this in a standard form to make it easier on us. So we're going to have VA. The only term on that is that we have a 1 over s. Convenient. And then we're going to right here we have minus 1 over s. I guess I'll write this as a plus. Minus 1 over s. Then we have a minus 1/2. And then we have a minus, I'm going to multiply an s on top and bottom here to get rid of this fraction. So we're going to have an s over 2s squared plus 1. And we're going to close that off, and it's all times VB, and this is going to equal to 0. So now we're going to get a single fraction down here, because again, it will be easier to work with. So we end up with 1 over s VA, and then we're going to subtract off here. The common denominator here is, oh man, so this is going to be 2s, so we're going to have 4s cubed plus 2s. So here we have minus 4s cubed plus 2s. Then we're going to have, oh, no, well, we don't need an s there because we already have an s on the bottom. We're just multiplying that by 2 times that, and we're good. So then we get, here we're going to multiply by 2s cubed plus s. So we're going to subtract off another 2s cubed plus s. And then finally here, we're going to multiply this by 2s. So we end up with 2s squared. And this is all going to be over 4s cubed plus 2s. Hope that's all readable. And this is all times VB equals 0. And then combining terms here. So we end up with, keep the 1 over s VA here. And so I'm just going to, instead of this being subtracted, I'm just going to pull it over to the other side because this is what we were going to do eventually anyway. So combining like terms, we have, 2s cubed. Should be a 2. It's horrible. Sorry. We have 2s cubed. And then combining the s squared terms, we have a 4s squared, and we have a, so this came from this last term here. So we have 2s squared, and that should be a plus because I put the minus out front. Wanted to make sure I get that right. So we have plus 6s squared, and then we have a single s term, and then we have a single 2. That's all divided by 4s cubed plus 2s, and this is VB. So now, remember that the thing that we weren't okay with was the fact that there was a VA in here. So what we want to do is we want to substitute that in. Remember, this is our first equation, and this will be our second equation. So we just want something for VA, so I'm going to multiply both sides by an s, and what that'll do is that'll cancel out one of the s's down here. So we end up with that. And so this is our second equation here. So this, actually, if you think about it, we can do VA divided by VB, and we will just have a term involving s's. So this is actually a transfer function to go from VA to VB. And so if we can then create a transfer function from u to vb, we'll be done because vb is vy. So giving myself some room again in order to do some math here for you. We're going to, so this way of doing things, going straight to transfer functions, is useful because it requires only algebra. But it does require you to have a good fundamentals of algebra. So if you are not too comfortable with your fractions and multiplying to get some weird polynomials and factoring, you should get comfortable with that before you attempt to do one of these problems on your own. But following along with me here, you should be OK. So what we're going to do is we're going to take this occurrence of VA, and we're going to replace it with this whole big thing times VB. So what we end up with is we end up with 4s squared plus 3s plus 1, all divided by 2s plus 1 times s. And we're going to replace this occurrence of VA with this big thing times VB. So we end up with 2s cubed plus 6s squared plus s plus 2. And so I'm going to leave this in factored form because multiplying this out for you is probably not going to be too helpful. But I will tell you something at the end to make sure that this all makes sense. And we have 4s squared plus 2 on the bottom here. And so that should be good. And then we have to, this is all times VB. And then so we subtract off 1 over s here. VB is all going to still equal to u of s. And so actually at this point, we're pretty much done. And even though it does not look very pretty, you can do some simplifications here. I don't have the simplifications ready. I apologize. I'll probably do this and post it in the description for you guys. But what I want you to get at here is that if we take this term here, and whatever our input is, we can, if we do 1 over this, we would multiply our input in the Laplace domain by 1 over this whole function here. And we would get our output VB. So I will combine everything for you here. Actually, this is not so bad. If I can, actually, I'll simplify this for you a little bit. So we have 4s squared plus 3s plus 1 all times 2s cubed plus 6s squared plus s plus 2. And then over here, we're going to subtract off 2s plus 1 times 4s squared plus 2. And we're going to divide this whole thing by 2s plus 1, s, and 4s squared plus 2. And so this is actually, because this is being multiplied by VB, we have a y of s here. And this is going to equal to u of s. And so what you can see here is we have exactly what we were looking for, our input related to our output by a multiplier. And so finally, we know that our transfer function is actually the input divided by the output. So we need to have the reciprocal of this as our transfer function. So this is going to equal to our transfer function, which we call h of s. And if we do this, we end up with 2s plus 1 times 4s squared plus 2. And again, these can all be multiplied out and simplified. I just don't have it ready. And I'll post what it is in the description. or in the comments below, one of the two. So we have 4s squared plus 3s plus 1 times 2s cubed plus 6s squared plus s plus 2. And then we need to subtract off our 2s plus 1 times, sorry, running out of room at the end of the board here. Okay, and so this one here is indeed our transfer function that takes us from our input to our output. And although this looks pretty complicated, you'll see here that this only has an s cubed term. This goes up to an s to the 5th. And this should have an s cubed term. So overall, if we are able to cancel out some things here, we'd have an equivalent second order system, which makes sense because these two being combined into one and this one combined here, we should only have really two things that matter to our output. So I hope that all made sense. It's a lot of algebra, but in the end, you end up with something that's very useful, a transfer function, which can perfectly describe how a circuit works. At this point, once you have this, you can find the output from the input without even knowing what's going on here. And it took a little bit of algebra to get there, but it is just using our basic circuit techniques and exploiting the fact that we have algebra for our current voltage relationships in the Laplace domain instead of the derivatives that are in the time domain. And also remember that all of this only works with initial conditions being 0. If initial conditions are not 0, we have a whole different set of algebra to go through because we need to subtract off that initial condition when we do our Laplace transforms. So in the end, we have our input and output related by a constant. And if we took the inverse Laplace transform out of that, we would get what we call the impulse response, which basically says that if I kind of just knock the system a little bit, if I give it a little like jolt to the system, if I give it at a single point in time, just a little bit of energy, how the system would respond. And we can use that to find how it would respond to any signal. So I hope you guys learned something. And if you have any questions, leave them in the comments below. We'll do our best to answer them. And have a nice day.